So first, hello everybody, and thank you for having us again. My name is Leandro. I'm here with Andy, and today we are actually here because at last SwiNOG gave us basically the last puzzle piece in our approach to network optimization. And in this talk, I will quickly give you the overall context and then hand over to Andy for a technical deep dive. So let's jump into the main core concept of our approach, the workflow as a transaction. And to motivate this, I brought a little example. So this is a very simple network changing operation. And I would argue it's quite a reasonable structure on how to do this. So the idea is to assert as many conditions as possible before we do a critical operation. And then in the end, we do some sort of health check to make sure that we succeeded. This looks nice and clean. However, there are still some issues or some challenges that we cannot solve within the script. The first one is interpretability. So this means that only the developer basically knows what an error means and how critical it is. And it would be nice to be able to derive something automatically. The second point is auditability. So in an enterprise context, it's always nice to know what changed when and what was the original intent for this change. And the last point, one of the most central one, is the race condition. And the race condition was one of our central points from our last talk. And we brought up this slide. I will just go very quickly over this. But our point was that even for such simple operations, it's quite hard to do them atomic. So whenever we do multiple of those operations in parallel on the same devices, we already can get stuck in inconsistent state. Another finding was that aiming for atomicity is basically an unreachable goal because as operations grow more complex, the harder it is to do this within a script. So the conclusion was that we need some sort of central coordinator. And we actually found, or we realized, that this problem is already solved. And it is solved in transactional databases. And there we have asset properties. We have our guarantees when a transaction succeeds or rolls back. And we said, OK, let's aim for that. Let's try to embed our workflow in an overall life cycle for a central coordinator. And do as many stuff that we can to make sure that we can guarantee a transactional behavior in most of the cases. And this is actually possible. One trick is to declare all the properties of the single steps. For example, pureness, or either potency or reversible. I'm sure you know more or less what this property means. Was one point of our last talk. But when we do this, then in most of the cases we can actually also bring these nice transactional models to the network automation world. And then of course there is always a little risk that we break a device or do something very wrong where we cannot just escape cleanly, and there we can still retain a lock because the transactional model uses a pessimistic locking approach, so we can at least make sure that when we break a device, we halt all the other workflows that potentially would run on this device, so a network engineer has some time to investigate. So this is our overall context, and from our side, we think, or from the software design side, we think we did everything that we could. So we have a lot of nice properties to do our function, to write our function blocks and to write our workflows. But we have still one central challenge here. And the challenge is that the quality of our system depends very much on the single steps, on the single function blocks. And here also with vendor agnosticity, it grows even more complex. So when we want to implement end-to-end testing in a vendor-agnostic world, then it's a lot harder than just test for one vendor. So we need to find some way to do that with as least friction as possible. And here came Netlab to the rescue, basically, from as presented in last SwiNOG. And Netlab is a very nice little virtual labbing tool that allows to write or declare a topology in a YAML file and then spawn a virtual network out of it. It can do much more, but this is a very clean interface for software engineers, so we can say which topology we need, and we can spawn it up. So based on Netlab, what we did is we designed an orchestrator workflow. And our orchestrator workflow has 3 steps. So we spawn up topology, we connect to it, we test our code, and then we shut it down. And what was missing from Netlab was basically to make sure we can orchestrate this somehow, so we can run Netlab in a powerful VM and make sure that each test case has exclusive access to this VM and to the corresponding lab. So this is the first point. Second point would be to be just dependent on the topology file, so we can bring the whole power of Netlab to automated testing in CI/CDs and IDEs and so on. And of course, it has to be simple. So the goal is to just use one simple Python decorator. So this is the broad context. I'm sure you all want to see some code. So let's hand over to you, Andy, so you can give a deep dive in how you achieved this.
Hello, I'm Andy. Thank you, Leandro, for the introduction to our general approach. So yeah, it was actually me sitting just somewhere over there last year at SwiNOG, actually being quite lost with my task of designing a testing framework for our whole workflow engine and function block concept. And then I heard this really amazing talk by Ivan Pepelniak about what they did with Netlab. And actually, when I dove into the documentation, found that it was the missing piece for building such a testing framework. So let's start the explanation first by defining our guinea pig for our testing explanation. So curious listeners might have seen the set admin state function block earlier on Leandro's slides. Anyways, this would be a simple function block, so a piece of code that sets the admin state on an interface on a device and is supposed to be vendor agnostic, and it would get a set of inputs, namely the interface and the desired state, and then deliver and perform the operation, and then give back a result. So the interface again, the state before, the state after, and whether it was successful, so whether we reached the desired state. So if we look into the code of this function block, it's actually quite simple. So we register it with this decorator with a bit of meta information. So we give it a semantic version and give it the idempotency flag, so that we can run it over and over again. And then the actual code would be that we fetch a connection for the device, then get the before state, run the operation, set the admin state, and then get the state after the operation, and then return the result. So actually quite simple with this one. And so if we would want to test this, the normal approach would be that we might have a unit test, for instance, which would run locally and test part of the logic locally. So for this quite simple testing approach, we wrote a decorator where we would just test the general logic with no device. So in our case, maybe we would want to have a test where we test that the function block fails gracefully if we get no device. But then this only gives us so many information about the actual functionality of the function block, so we might actually want to test this against actual devices, or in our case, actual virtual devices. So for this, we came up with a decorator which gets fixture, which actually just is one of these YAML files Netlab takes, wrapped in a PyTest fixture with some logic we provide. Then it gets some parameters, and in this case, runs the function block against the Cisco IOL device of this topology and asserts that the port is down after we perform the operation. And then we also might want to test this function block against another vendor, in our case here, a Nokia SR Linux device type, and there we would just pass another fixture and another assertion. So in this case, we want to put the port up and assert that it's up after we perform our operation. So if we dive a bit into the Cisco IOL case, when we define the decorator and then run PyTest, it discovers the test generated from the decorator, then connects to our remote lab service, the orchestrator Leandro was talking about. And this then utilizes Netlab, and in these cases Containerlab, to spin up the topology and give us back a virtual lab with actual virtual IOL devices. So parts 1 and 2 could run anywhere, so locally in our IDE with breakpoints like we know from other debugging or from debugging other code. And 3, 4, and 5 usually would run on a VM in the cloud, or maybe also on our local Linux, Ubuntu Linux computer for testing. So that you see that I don't only talk theoretical. On the left here we have the code we were just talking about with all these decorators and our function block on the bottom. And then when we actually run these tests, there's a few screen caps from that. The upper one would be the unit test, which is actually really fast and simple, and the lower ones would be the actual tests running against the lab. So we see the lab spawn, and the test in the end turns green. So if you paid close attention, we twice mentioned the term vendor-agnostic, which I think usually is a quite overused marketing term probably, but for us it was actually a necessity to have our testing effective for multiple vendors, and also to abstract our function blocks away from networking scripts, which might rely on complex if-else cases and be very fragile with different vendor types. So actually, when we execute this piece of code, we fetch the connection through what you see here called as an admin state proxy. So this is just a piece of code which implements a capability. So actually just an abstract class providing the interface for what we want to do, so fetching admin states or setting admin states. And then the proxy would route this to the correct plugin for the vendor type. So for iOS devices, it might route it to this simple iOS plugin using Scraply for executing the commands. And for the Nokia SR Linux devices, it might route to a NetMiko plugin for SR Linux devices, which implements this capability and execute the relevant pieces of code or commands on the SR device there. And if we would want to integrate not just another vendor, we would just write another plugin and use any connection library we want, and just define the logic with that connection library and have another vendor up and running. So after we implemented this, the actual fun starts using this approach. So what would this give us? So we would get CI/CD for the network, so we can run this in our GitHub Actions pipeline, have the actual tests be green, and know the function blocks work against all these vendors we wrote tests for. We can actually debug this like any other code, so we can just run this in our PyCharm or VS Code and put breakpoints and test on actual devices, not only logic on our own device. And if we would add a new vendor, we would have the same function blocks running just with another plugin. Then if our AI wrote function blocks, it could just spin up a test and get feedback if it works or iterate over it again. And then hopefully you can refactor without fear, or at least less fear with this approach, and eventually hopefully sleep better.
Cool, thank you, Andy. So what's next? Really quick. We actually decided to make this open source. So we published just last week the developer preview for the Remote Lab. Expect some rough edges, but expect integration of Netlab into PyTest, so you can easily interact with those virtual labs. And yeah, we call it the last % for fully automated, realistic end-to-end testing with Netlab. Thank you very much.
Thank you.
Thank you. Questions?
Achtung.
Just a remark. Great job. Thank you.
Thank you.
Thank you, Ivan.
Okay, thank you very much.